Welcome back. What we're going to now talk about is what do we do with situations involving what we call free fall, which is having an object move through the air, and how do we solve those problems. Free fall is an extension of what we've done so far with kinematics, and you might be thinking to yourself, okay, so we've done all these graphs where the acceleration is constant, but that's not really how most events happen in terms of motion. So why are we learning about this sort of special case where acceleration is constant? And it turns out as long as things are relatively dense and the speeds are not too high, things in free fall generally have a constant acceleration. Another situation, as long as friction is not too high, is anything moving down an inclined ramp also generally has constant acceleration. So part of the motivation to do all of this study is to prepare us to handle situations where objects are either in free fall or moving up or down an inclined ramp. Let's go ahead and talk about one of the beginning experiments that worked through this idea. So this idea of free fall, and that there's a constant acceleration and that we might be able to find that constant acceleration, started in part with experiments done by Galileo. So here's a mock-up picture of what his experiment might have looked like. What Galileo thought about is the fact that it's really difficult if you take an object and you drop it to try and track the motion of that object. It happens too quickly, and there are a lot of factors that make it hard to track the motion. But what he recognized is that if you take an object and put it on a ramp, and if that ramp is flat so that the angle isn't changing, the object seems to accelerate in a very similar way as if the object was simply dropped vertically downwards. Now, he didn't, unfortunately, leave behind really a record of his total experimental apparatus, so there are a lot of different educated guesses on how he actually measured and set things up, but this mock-up gives us a nice idea of things. In this mock-up, what he has is he has bells here that go from the top to the bottom of the track. His ultimate goal was to figure out where to place these bells so that they rang in approximately 1-second intervals. Now you might be wondering, how is it that he could figure out the 1-second intervals? Again, we're not entirely sure as far as my understanding goes. We think he either used water droplets falling to try and time things, or he used a pendulum with a known 1-second timer. Regardless, what his goal was to figure out how can he measure the distance the object falls in consecutive seconds, and try and figure out, is there a relationship between that distance between each second, and can we find a mathematical relationship here? What he found was that there was actually a pattern to the distance that the objects fall. So in this, we'll just use this mock-up example to help illustrate the pattern. Notice in the first second, we can say for this angle, the ball falls 1 centimeter. The ball then falls a total of 4 centimeters, so this is the first second. In 2 seconds, then, the ball falls 4 centimeters, which would be 1 centimeter plus 3 centimeters. Then in that third second, it falls for a total of 9 centimeters. So we have 4 centimeters plus an additional 5. And then for the next second, it has now fallen a total of 16 centimeters, which is 9 plus 7. So hopefully you're starting to recognize there's a pattern here. Notice how the ball is falling in this pattern where it's 1, and then plus 3, plus 5, plus 7. It's this weird pattern of odds. So we might think the next distance it would fall would be plus 9 centimeters. And the reason that's important is it helps us to recognize the fact that that distance it is traveling is increasing at a constant rate. Which means if we were to make a velocity versus time graph, that the velocity is changing at a constant rate, which is what we've been working through so far. What Galileo then did was took that time interval and compared it with the height that it had fallen to try and see, was there some sort of relationship. And it turns out that there is. So in this case, what we have here is we have time on the y-axis and height on the x-axis, which, from my understanding, is how he examined the two variables. What I would rather do is put them on flipped parts, so the time on the x-axis and the height on the y-axis. And instead of getting this x to the 1/2 shape, when we flip those, we get an x squared shape, which looks like that. So notice that this is a position versus time graph. And so the velocity versus time graph would look like that. It would be linear. So we found, or he found, that there was in fact a constant acceleration for objects on an inclined plane. And then his next goal was to start to figure out here sort of what is this constant of free fall that we have going on. Now let's go ahead and look at this idea with a track that we used in our previous experiments in the cart. And this time what we're going to do is incline the track and see how it is that we might record that acceleration down the track. So in our last lab and then in our discussion, we looked at the motion of the cart as it accelerated constantly, where the motion change was caused by this fan. And so one of the things that we want to start to focus on here is these cases where we have acceleration are always connected to the interaction of the system, in this case the cart, with something external to the system. There must be something that creates a sort of a net change to the system, and we call that thing an agent. So in the last experiment, this fan was the agent. Now this time I have the ramp here on an incline, and I'm going to take the fan away, and this time instead I can generate the same sort of motion without having a fan, because there is something that will act on this cart. Now usually we would say what acts on this cart is gravity, and I'm going to be a little nitpicky about that. The first thing we want to say is the thing that acts on this cart is not gravity, it is the Earth, and it is in particular the gravitational force caused by the gravitational field of the Earth. So the agent acting on the cart this time that will cause an acceleration is the Earth acting through a gravitational force. So just like with the fan, if I give a push to the cart up the track, it will uniformly slow down and then speed up as it comes to a stop instantly and then falls down. Or if I simply let go, it will speed up. Now, as we just mentioned earlier in the video, Galileo proposed an experiment in which he wanted to see what's the relationship between the acceleration of an object due to the Earth acting on it and its motion. Is there some sort of relationship that we can determine? So what we're going to do here is turn on the motion sensor and let this fall. And we'll start by looking at what sort of motion graphs do we get and what can we notice from that data. So far here we have the position versus time and velocity versus time graphs. And some important things should stand out about the shape of this graph. First, what do you notice about the position versus time graph? Before we hit the chair down at the end and it stops, notice we have a quadratic shape, right? We have a parabola to the position versus time graph, just like we saw with the fan cart. The velocity versus time graph then has a linear shape, right? It is increasing in the positive direction, but at a constant rate. So the first important finding that Galileo did with his experiment was to notice that there was a relationship between the acceleration and the time and the position, where the position changed as a function of the time squared. We had a y equals x squared shape to the data. Since the velocity has a constant slope, what we can do then is find that slope value to start to figure out what is this acceleration caused by the Earth. So let's go ahead and do that. So just as we would hope to see, the acceleration, look how nice and constant that data is for this motion. Very constant acceleration as the object falls down the ramp. And the slope of the velocity versus time graph at 0.62 meters per second squared is very close to the mean of the acceleration versus time graph at 0.64 meters per second squared. So this is data for one incline. And what Galileo then posited as his next step is, would this relationship hold true if we increase the angle? And would there be something noticeable that relates the angle with the acceleration of the object? So first, just consider for a moment, if I take this cart and move it from the first rung here of my chair up to the second rung, what do you think will happen to the value? Let's go ahead and do that and take a look. So we increase the angle, and notice how now the slope and the mean are both about 1.3 meters per second squared. What Galileo did was recorded the height of the elevation, or the height of the fall, so I could measure from the bottom of the chair up to the starting point to find my change in height. And then also, what is the change? You could do one of two ways, right? What is either the change across the length of the track, or what is the horizontal change? In this case, he used the length of the track. So this track is 2.2 meters. And then we can figure out here what's the relationship between this angle and this new acceleration value, right? And what we can do is continue to increase our angle. I can go higher and higher and higher up to the top of the chair, or even higher. And what we want to think about next is, what is the steepest that we could have this cart fall? What is sort of the limit where the cart would accelerate at its greatest rate, and we could never really increase that just using the Earth and its gravitational field? And the answer would be to simply drop it, right? Have it fall straight downwards. And that would give us our greatest value for the acceleration. Let's talk more about what that value is and how we could find it using this track experiment. So if we were conducting a full experiment, what we could do is change the angle by some increment, right? Maybe every 5 or 10 degrees, collect data, and then start to figure out the relationship here. Now for each set of data, we would have a velocity versus time graph with a constant acceleration or a constant slope. And so we would see with each angle, we'd have a change to this graph, or a change to these acceleration values. But what we would want to look at is what happens with this h over L piece as we change things. And if we were to plot a graph instead of this ratio of h over L and the acceleration value we determine over here, what we could then do is figure out what is this constant. And this constant would be this free fall value. The other thing we want to figure out is, what does this h over L mean? So think about the fact we have this ramp, and this ramp is inclined, some angle theta, right? And we have some fall, h, and some length we travel, L. Now, if I had the height equal to 0, I would have a flat track, right? And so as a result, I would have no motion. So the angle here would equal 0 degrees, and then I have no acceleration, right? And the steepest I could make the track would be vertical. And in that case, we'd have h equal to L. So my theta would be equal to 90 degrees. And so h divided by L would equal 1. And I would have the greatest acceleration. Now this happens to be a trig function, right? Which trig function relates the angle with the height and the hypotenuse, the opposite leg and the hypotenuse? And that is the sine function. So the way we can find the acceleration of an incline is actually to take this free fall value that we'll talk about in just a minute and multiply it by sine of the angle of the incline. So this is a really important equation that you want to have. We will see in forces more of where this comes from, but it's really important right now that you have this equation and you keep track of it as we keep on working, and we will need this in the fall when we start work. Now let's take a look at where that quadratic relationship comes from between position and time, where we saw that there's, for that position versus time graph, a parabolic shape as the position changes as a function of time. Remember that the position equals the area of the velocity versus, or excuse me, the displacement equals the area of the velocity versus time graph. So we could initially say an equation for this position as a function of time, assuming that x initial equals 0 meters, right, is equal to the area of this triangle, which would be 1/2 of v final times whatever our time interval is. Now remember, we talk about when we don't know something, in this case we don't know v final, what we can do is substitute v final for with our acceleration equation. So in this case, remember that the acceleration equals delta v over delta t, And the acceleration equals the free fall value, this constant, times sine of the angle. So what we can do is say that the v final, since v initial is 0, this delta v simply equals v final, is equal to this acceleration. I'm just going to put f sine theta times delta t. So if we substitute this in, then we get an equation that shows us where this quadratic comes from, where the change in position, or just x final as we said, equals 1/2 times this free fall constant times sine theta. So all of these are constant for one scenario, times delta t, or delta t squared. All right, and so that's where that quadratic piece comes from. Constant that I've referred to is eventually given this symbol of a lowercase g, and it is technically a vector. And the value for that acceleration is approximately 9.8 meters per second squared. And that was something that was initially found via experimentation. It wasn't something that we were able to obtain theoretically, but instead by conducting experiments like Galileo's experiment, we came up with a better and better value that is around 9.8 anywhere near the Earth's surface. About this free fall acceleration and this value. So we use this lowercase symbol, this little g. It's really important that you use a little g because later on a big G will come around. Its value on Earth is in general 9.8 meters per second squared. If we wanted to be a little more precise, it would be around 9.81. Now the units. Notice in this scenario we're talking about acceleration, so we start by using these units of meters per second squared. The problem is that this g really isn't free fall acceleration. It's merely by coincidence that it seems to be the free fall acceleration. And this is a misconception that people develop very frequently. Instead, the units that you need to put in your notes are this n divided by kg. Now, what are these n? We'll talk more about these next unit. N stands for newtons. And it is a unit of force. So we abbreviate it capital N, and it is a unit of force. So for now, please just bear with me. Just write that it really is 9.8 newtons per kilogram. And let's talk a little bit more about what that represents. What happens with this value of 9.8 and people writing that the units, instead of being newtons per kilogram, instead meters per second squared, is they call it two things that really are not a good term to use. The first is gravity. People will say that this value g is gravity. That is a really bad thing to learn. So please do your best to cut that out of your mind. It actually represents what is called the gravitational field, which is something that we don't really have a concept of because we can't see fields. The only field that you might have seen before is a magnetic field. You might just Google it if you haven't, but generally what we do is we take a bar magnet, and you might have done or seen the experiment before where you put a bunch of iron filings nearby, and you get an apparent pattern that goes around that bar magnet. Those little filaments, the filings of iron, are showing you the path of the magnetic field. This g is the analogous thing for gravitational force, and it is called a gravitational field. So if you start to learn that this is a gravitational field, it makes learning about electricity and magnetism a lot easier because you have analogs. So it's just a coincidence that this gravitational field happens to be the same thing as the acceleration value of something in free fall. It's a coincidence. Please don't memorize this as acceleration due to gravity. That's another term a lot of people use. That's not really the best idea for this value of g. So g, as we'll talk about more in forces, is the value for the gravitational field near the surface of the Earth. Key points about g. First, it's newtons per kilogram. It's just a coincidence that the units are also meters per second squared. The value is approximately 9.81. However, on the AP exam, they've now said that for all parts, both multiple choice and free response, you may round that to 10. So obviously, when you're doing an experiment to get the best possible prediction or result, you really need to use 9.81. But when doing a problem where you're short on time, use 10. The other thing we need to talk about is direction. So a gravitational field always points towards the center of the Earth, which appears to be downwards from our perspective. So the way you can tell is to take anything with mass, like my pen here, you drop it, and any object with mass will move in the direction of that field. So that's always towards the center of the Earth. As a result, what you need to make sure that you remember is that any time an object is let go, thrown upwards, or thrown downwards, always, 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 the direction is down and the value is 9.8. So a big misconception mistake that students make is they assume when I throw this upwards that initially, as soon as it leaves my hand, the acceleration is still up. As soon as this pen leaves my hand, the acceleration is down, which is necessary for this pen to be slowing down. So beware trick questions where it will make it seem like the acceleration is up, even though my hand is no longer there. Solving these problems, we will often say that air resistance is negligible. It's a really helpful strategy to simplify problems. You want to often remember that in science and in math and in any other field, it's really helpful to think through a problem in simpler terms before you make things more complicated. And this isn't like a cheat. It's not something that you want to think of where we're faking things, because it turns out that it's often a reasonable assumption. As long as something's going about 45 miles an hour or slower, it really air resistance really doesn't have that significant of an effect. And we'll look at sort of a proof of that later on in the year. But for now, just take my word for it that as long as an object isn't going really fast and is reasonably dense, air resistance can be negligible. Now let's look at an example of experiments that verify how this objects can fall at the same rate. So for the Apollo 15 mission, what they did is they took a hammer and a feather up to the surface of the moon and recorded dropping them together at the same time from the same height. I know it's a bit grainy because this is from a long time ago, but did you see how the two objects fell at the same rate? A neat little verification of this prediction that objects should fall at the same rate. Experiment that you can find the full video for on YouTube is they took a feather and a bowling ball and put them in a gigantic vacuum chamber. I think it's NASA's vacuum chamber. But anyways, let's take a look at that. They dropped them at the same time and notice that in a vacuum the feather does fall at the same rate as the bowling ball. Pretty neat verification there. The motion graphs would look like for an object in free fall. In this case, we are going to make sure to note that the positive y direction will be up and the positive x direction will be to the right. I could do this with the positive y direction down, and it's important to note that these coordinate systems are always just constructs. You make them what is convenient to you. So if I drop an object downwards, the position versus time graph then would have an object that starts out at rest, right, and speeds up in the negative direction. So it would look like that. If I flipped the coordinate system so that the positive y is down, then I would simply have a graph that looks like that. The key is that for both of these, it is a parabola. It's a quadratic. So the velocity versus time graph then needs to show the object speeding up with uniform acceleration and would look like that. As a result, the acceleration versus time graph looks like this, where the value here would be a negative g. Now this happens to be the same as what we would see if we dropped an object down an inclined ramp. We would just have some value less than g, right? Remember we said that the acceleration down a ramp is equal to g times sine of the angle of the incline of that ramp. So what about if we instead throw the object downwards? So if we throw the object downwards, we are now giving the object an initial velocity in that direction. So if we again set positive y to be upwards, then for our three graphs here, I think it's easiest to start with our velocity time graph. The object is again going to accelerate downwards, but it is starting with a non-zero velocity. So it would look like this. Now, an object that is dropped downwards should be parallel. It should have the same slope. It just has a lesser initial velocity because the initial velocity would be 0. For both of these, the acceleration would be negative g. So a key point here is that when you throw an object versus dropping an object, the acceleration for both of them as soon as it leaves your hand is g, downwards. The only difference is where they start on your y-axis. So for the position versus time graphs, remember we said for the first one, we would have a graph that would look like this as we would speed up in the negative direction. So instead, all we would have to start would be starting with a steeper line. So that way, we're starting at a non-zero velocity. If we throw an object upwards. So if we throw an object upwards, we have initial velocity upwards, but we have that acceleration downwards. So let's start again with the velocity versus time graph. This time we start with a non-zero positive velocity, and that's going to decrease as the object slows down. The velocity will then increase in the negative direction. So a key part here, a thing that students often make a mistake on, is that the acceleration for this whole motion is still a negative g. Is still a negative g. So it doesn't go from positive to negative, or maybe from negative to positive. Nope, it is always this value here. The position versus time graph is then going to look like a parabola. So to start, it moves with positive velocity, but it slows down, and then it moves with negative velocity as it speeds up. And we get a parabola. So the big key idea here that I want to highlight is that this slope for the whole motion is constant, and so the acceleration is constant. It's just in the beginning part, we have positive velocity, so we slow as the signs are opposite, and then we speed up after we come to rest for that one initial moment right here where our velocity at that instant is 0. What we'll do is work through some conceptual questions to make sure we're comfortable with the concepts here. First, let's say we have an elephant and a mouse dropped from rest at the same height at the same time. Which will reach the ground first? So as long as we can neglect or ignore air resistance, they should fall at the same time. Right? All objects fall with an acceleration value of g. We have a bowling ball that is dropped out of a 12-story apartment building. And I have a typo. Please ignore my typo. Not apartment build, apartment building. As it falls, what happens to its speed? So the object starts from rest, right? V initial is 0, it is dropped, and then that velocity will increase. So the graph of velocity versus time might look something like that. So as a result, it cannot fall at a constant velocity. It must speed up the entire way, unless we have air resistance. In that case, it would reach a maximum speed and stay constant. So this would be with air resistance. But otherwise, if we don't have air resistance, it will simply keep speeding up the entire way that it falls. And this is a reasonable approximation for this sort of scenario. A bowling ball is really dense. It's not going to be falling too fast, and so it really will continue to speed up with an acceleration value of g. So let's say we take an object and we drop it, and we set the positive direction to be upwards. For our velocity versus time graph, and our acceleration versus time graph, we want to think about what would the sign of the acceleration be. So the velocity starts at 0 and it's going to speed up in the negative direction. So I have a negative slope, right? And that means that I have a negative acceleration value. Remember that the sign of the velocity must have the same sign as the slope to speed up. So our answer would be B. The acceleration is negative. Instead of dropping, I throw the object straight upwards. So to start from my velocity versus time graph, I would have a positive non-zero value for the velocity, so long as we make the positive y direction up. The question is, what is the sign of the acceleration? So as the object goes up, what will it do? It will slow down, right? So my velocity is going to go to 0, and then once it reaches the apex of the motion, it will speed up in the negative direction. So if I have a negative slope for this velocity versus time graph, then my acceleration versus time graph must have a constant negative value. Remember, whether you throw an object up or down or drop it down, it always will have an acceleration directed downwards at a value of g. Few practice problems. First, we have a rock that drops for 5 seconds starting from rest. About how fast will it go after 5 seconds? So what we can do is use our equations from earlier in the unit now and simply apply them to freefall. So we know that the acceleration for an object in freefall is g, and so g must equal delta v divided by delta t. So if we have delta v is v final minus v initial, and that's going to equal g times delta t, and v initial is 0, then that means that we'll take these 5 seconds, and remember we're going to use that g is approximately 10 meters per second squared, or remember the actual units that we want to be keeping in mind is 10 newtons per kilogram for later on. That would be approximately 50 meters per second. Throw a ball straight up and catch it when it comes back down. At the highest point of the motion, how fast is the ball going? So it's really important to think about this motion in terms of graphs. We have position and velocity and acceleration graphs. Remember, for the acceleration graph, it is a constant value of negative g. So what that means is for the velocity, the object starts moving upwards and slows down until it comes to a stop, and then it will speed up. And so our position versus time graph would look like this. So at the highest point that we have here would be right here. Our slope there is 0, which matches this x-intercept. So at the highest point, for that one brief instant in time, the velocity is 0. Here's an example of a question that's easier to answer if we think about it in terms of motion graphs. If I throw a ball straight up and then catch it at the same height at which I threw it, how does the time up compare with the time down? So for the velocity time graph, it's going to start moving upwards and slowing down, right? And then will speed up as it moves downwards. Now, the displacement up is equal in magnitude, just opposite in direction with the displacement down, right? So that means that this area of the graph should be equal in size to this area of the graph. For the position versus time graph, then, what that means is that the shape looks like this. It is a parabola, right? And it's not just a parabola. A key thing to remember back from algebra, you learn about symmetry of graphs, right? So it turns out the important thing with parabolas is that they are symmetric. So this parabola here is symmetric, where I have this starting point and this end point the same, which means that this time here is 1/2 of the total, and this time here is 1/2 of the total, and therefore the time up is equal to the time down. It's very helpful to think about motion in terms of motion graphs. So if we continue this thought, this time, when we throw the ball straight up and catch it at the same height at which we threw it, let's think about how does the ball's speed at the beginning compare with the speed at the end. So remember the position time graph we just said looks like this. And so for the velocity versus time graph, it needs to be symmetrical in the sense not that we could draw a line down and they'd overlap, but that the slope here at that instant is equal in magnitude, just not in sign, to the slope at the end. Meaning that this speed here to start will be equal in number, if I took this absolute value, with the velocity at the end. Another way to think about that is that the time which it slowed down is equal to the time which it speed up. So let's say that this time here is 3 seconds. Then for 3 seconds, I have an acceleration of -10, which gets me from 30 to 0. And then I'm going from 0 for another 3 seconds, now speeding up with this -10 meters per second. And so I will end at -30. So if I started at +30, I end at -30, then they have the same, and it is not 0. as long as we ignore the throwing and catching part and just moving through the air part. Another important conceptual check here. If I throw the ball straight up and catch it at the same height at which I threw it, at the highest point, apologies for the typo here, not working on much sleep with the baby. At the highest point, what is the acceleration of the ball? So remember, this is a trick question. The velocity versus time graph looks like this. So there is never a moment where I have a positive slope. There is never a moment where my slope is 0. Right here, when it's at rest, I still have a negative slope. So the acceleration is always 9.8 meters per second squared down. Let's work through how to work with some numbers here. Turns out that because this is again constant acceleration, you can use the kinematics pies method we've talked about to solve problems with free fall, as long as you just remember that the acceleration equals g, or if we are on a ramp, then the acceleration equals g sine of the angle of the ramp incline. So let's say we drop a stone from rest off a 45-meter tall bridge. It hits the water after 3 seconds. How fast is the stone going after 1.5 seconds? So for the velocity versus time graph, right, we start at rest and it's going to fall with a slope of -10. So what that means is after 3 seconds, we said that we would be at 30 meters per second. So if this slope is constant, then after 1.5 seconds, we would have a velocity of 15 meters per second down, half of the stone's final speed, because that is a linear relationship. Next question is, how far will the stone have fallen after half of that time? So remember, for our pies method, we think about this in terms of velocity versus time graphs. So the displacement here in this first 1.5 seconds is equal to the area here of this triangle. So that vertical displacement would be equal to 1/2 times the velocity at 1.5 seconds times that time interval. So we would do 1/2 times, we said that speed was 15 meters per second, times a time of 1.5 seconds. So if we look at this, we want to see, is it less, more, or equal to half of that total fall? Right, 1.5 of 15 is 7.5. Times 1.5 is most certainly going to be less than 22.5. And so as a result, in the beginning, we fall more slowly. Right? Remember back to Galileo's experiment that displacement per second increases by that odd amount. And so in the beginning first half, we're going to travel less distance. And as the object speeds up, each second it will travel a greater and greater piece. We see that here with the area of the second piece. In the area of the second piece, I have the same triangle here as right here, plus this whole new area here. Pies method sort of problem here. Now we drop the object, same scenario as before, and the question now is when the object has fallen 22.5 meters, half of the height, how fast is it going? So remember, we always make a VT graph. And this time what we know, besides the fact it starts at 0 and it has a slope of -10, we know that in this unknown time interval, we have an area here for this vertical displacement equal to 22.5 meters. So that 22.5 meters equals the 1/2 v final delta t. So what do we know for that? We don't know v final and we don't know delta t. So remember, when both of these things are unknowns, what we do is substitute in our acceleration equation. A equals delta v over delta t, which in this case equals g. So I want v final, so I want to get rid of delta t, and delta t is equal to the change in velocity divided by g. So we have 22 meters equals 1/2 of v final. And remember that this delta v is v final minus v initial, and v initial is 0. So we really have v final times v final divided by g. And now what we can do is solve for v final. So first I'm going to move the 1/2 over. So I have 2 times 22.5. And then I'm going to multiply by g. And that equals v final squared. So v final would be the square root of these things. Right? 2 times 22.5 is 45. If we make g 10, then that's approximately the square root of 450. 15 squared would be 225. And so this 450 is greater than that. So the speed will be greater than 15 meters per second. A little more practice here. We have a piece of hail moving at 20 meters per second. And 3 seconds later, how fast will it be moving, assuming it doesn't hit the ground? Remember to always model things in terms of velocity time graphs. So the hail is moving at 20 downwards. And so whether something is dropped or thrown, the slope is always this negative g. So it really doesn't matter for this 3 seconds later, the change is the same for each piece. Right? We have 3 for the time times g will give us delta v. So 3 times 10 is 30 in the negative direction. So we'd have negative 20 minus 30 equals a new velocity of negative 50 meters per second. So the speed would be 50 meters per second. Build on this question and this concept here. Let's say I drop a rock off of a bridge, so it will look like this. And then I throw another rock straight down, so it has a starting velocity that is not 0 and is downwards. Which of the rock's velocity will change more quickly? So remember, this is a trick question. They both have a slope of negative g. So the rock that is thrown will move downwards with a greater displacement each second. However, they both will have the same change in their velocity. Remember that this change in velocity per change in time will equal negative g for both cases. Final question here that actually becomes a pretty easy thing to calculate if you make g equal to 10. You can get a pretty rough approximation. You want to know how deep something is. You're standing over a well, and you drop a rock and find that you hear a splash after 3 seconds. How deep is the well? So remember here that what we always want to do is think about what do we know in this problem. We know that v initial is 0. We know that the time of this fall is 3 seconds. And we know that the acceleration is equal to g downwards. So as a result, what we can do is make a velocity time graph that models that information. And if we want to know how far we fall, that vertical displacement is equal to the area of this triangle, which is 1/2 of v final, which we don't know, times the time, which we do know. So we want this. We know delta t, but we don't know v final. So what do we do when we don't know v final or something else? We use the acceleration equation. Right? Acceleration equals g, which equals v final minus v initial over change in time. So v initial is 0, and we can say then that v final is equal to g delta t. So if we substitute, we have 1/2 g delta t times delta t. And now we have all the information we need to figure out that vertical displacement. Right? We're going to do 1/2 times approximately 10 times 3, which is 9. So 10 times 9 is 90. 1/2 of that would be 45 meters. So we can then estimate that the well is approximately 45 meters. Probably a little bit less since we rounded up to 10 from 9.8, but pretty close to that number. So that's it for Freefall, and that's it for the concepts that we need to know before we start the school year for kinematics. As always, if you have any questions, feel free to send me an email. Otherwise, I hope that this was helpful. I hope that this was done in a way that made sense to you. And if there are questions that you have that you would like clarified, I'm also happy to work through those in the fall. Just let me know ahead of time so I can plan and do my best to help you. Otherwise, thanks for watching, and have a great rest of your day.